Hi everyone, I'm Adrian. I'm a postdoc at Princeton University and at the Flatiron Institute at Simons Foundation. And today I'm going to talk to you about some of my work on measuring neutrino mass using nonlinear cosmic structure. But before I talk about nonlinear cosmic structure, I want to put my particle physics hat on and review how accurately we can measure the neutrino mass in particle physics. So to start the review, the first evidence for neutrino mass was from neutrino oscillations, and there are two key experiments relevant there. So first of all, there's the atmospheric neutrino experiments, which measured cosmic rays interact with the atmosphere, produce muon neutrinos, and then these muon neutrinos would travel through the Earth and were observed on the other side of the Earth, and it was found that there were fewer muon neutrinos than you'd expect. And so this suggests that neutrinos oscillate, they change flavors, and if they oscillate and change flavors, this means that they must have a mass. And then similarly, there were solar neutrino experiments, which observed that there were fewer electron neutrinos than you would expect because the sun only produces electron neutrinos when it does beta decay. And because there were less electron neutrinos observed at Earth coming from the sun, it suggested that they oscillate and therefore neutrinos must have mass. But neutrino oscillations only tell you about the difference of masses in the different mass eigenstates. So what the neutrino oscillation experiments tell us is that there could be two different hierarchies of neutrino masses. You could have the normal hierarchy or the inverted hierarchy. In the normal hierarchy, there are two very light neutrinos and one heavier neutrino. And in the inverted hierarchy, there are two heavy neutrinos and one lighter neutrino. But the key point is that neutrino oscillations don't tell you the absolute mass scale. And so if you want to measure the absolute mass scale using particle physics, you can use beta decay. And this is something the Katrin experiment has done. And so in beta decay, a neutron decays to a proton, electron, and an electron antineutrino. And because this is a three-body decay, if a neutrino has mass, it will take away some of the energy of the electron, and you can measure the energy distribution of electrons, measure the maximum energy that an electron has, and based on that, you can infer how heavy the neutrino is. And so far, Katrin has got constraints of 0.8 eV as a maximum for the neutrino mass. Should go down soon, but that's where we are right now. And so what we have in terms of particle physics right now is oscillation experiments giving us a lower bound of 0.06 eV and beta decay experiments giving us an upper limit of 0.8 eV. And cosmology can help bridge this gap. And the way cosmology does this is, first of all, here's a picture of the Big Bang. You have the Big Bang on the left and the CMB, and then the expansion of the universe and all of large-scale structure. And so the CMB, light from the CMB, travels through the universe in order to reach us today. And so just by observing this light, if this light travels through a background of the universe, which has massive neutrinos, then the light will pick up a signal due to massive neutrinos, and you're able to measure the neutrino mass from this. And this is something that was done by Planck in 2018, and they got an upper limit on the neutrino mass of 0.26 electron volts. But then another effect that neutrinos have is on the clustering of matter in the universe. And so while cold dark matter tends to cluster and form halos, neutrinos are much lighter particles and therefore have much higher thermal velocities, and they don't cluster. It's much harder for gravity to make them cluster. And so this also leaves an imprint on the CMB and on large scale structure. And so by combining the CMB information with large scale structure information, for example, in CMB lensing and with BAO, you can get even tighter constraints using cosmology. And so in terms of stage 3 experiments with CMBxLSS, the upper limit on the neutrino mass was 0.12 eV. So really pushing down the upper limit compared to particle physics. And so there's a lot of great experiments on the way in terms of cosmology, measuring large-scale structure and the CMB, but pushing to smaller and smaller scale. So what I showed you before is mainly looking at large scales, which are well described by linear physics. But these new experiments will push to smaller and smaller scales, higher and higher resolution, and probe nonlinear effects of neutrino mass. And so in the remainder of my talk, I'm gonna tell you about what kind of effects neutrinos have on these nonlinear scales. And to start with, let's just look at large-scale structure. How much information is there about neutrino mass in large-scale structure? Well, first of all, let's look at linear theory. So linear theory is well understood in terms of the power spectrum. And you can see in this plot, the power spectrum as a function of K, that as you increase the neutrino mass from 0 to 0.3 to 0.6 to 1.2, there's this suppression of power on small scales. And this is because neutrinos don't cluster as much as dark matter on small scales, as I discussed in the previous slide. But small scales are nonlinear, so using the linear power spectrum on these small scales isn't accurate. And future surveys will probe these kind of small scales where nonlinear physics is relevant. And so we need a way to model the nonlinear effects of massive neutrinos in order to study them. And the way to do that is using simulations. There's various different ways of doing neutrino n-body simulations. One approach you can take is the linear response approach, where you put the neutrinos in the CDM equations without actually simulating particles of neutrinos. You could also include particles of neutrinos and do a hybrid approach between this linear response approach and using particles. You can also just use particles or use a phase-space approach. There's a lot of different things one can do here, a lot of different options, and I'd be very happy to discuss this later. But for now, I'll just say that there are these simulations that exist, and what these simulations give you are these beautiful pictures of matter and neutrino clustering in the universe. And so on the right over here, we have delta C, the overdensity due to cold dark matter. And then on the left here, the neutrino overdensity. And you can see that the cold dark matter density is a lot more clustered than the neutrinos because, as I said earlier, cold dark matter clusters much more. And then when you combine these two together, the cold dark matter and the neutrinos, you get the total matter density on the far left. And so in the remainder of my talk, I'll look at the different information content in these different fields. And to start, let's look at delta M, so the total matter over density. Well, first of all, if we want to measure the amount of information in a cosmic field in the nonlinear regime, we have to move beyond the power spectrum. Traditionally, cosmologists use the power spectrum to extract information from cosmic data, but in nonlinear scales for non-Gaussian maps, this is no longer optimal. It no longer tells you all the information in the field. And so one way to move beyond the power spectrum, to move beyond the 2-point information, is to include higher order statistics. And two such higher order statistics you could look at is the halo mass function. So this is a histogram of the masses of halos in your data. Or you could also look at the void size function, which looks at voids, these empty regions of space, and makes a histogram of how large they are. And by using this information in conjunction with the 2-point information, you can get even more tight constraints on neutrino mass. So what this plot is showing over here is you have the 2-point correlation function as the red contour, and then the halo mass function is the blue contour, and the void size function is the green contour. They all have very different degeneracies in the neutrino mass sigma 8 plane. And so when you combine them all together, you get this really small black contour and therefore really tight constraints on the neutrino mass. You can see that it's almost 100 order of magnitude more constraining when you combine all three statistics compared to just using the power spectrum on its own. So what this is saying is that there's really a lot of information in the matter field about neutrino mass. One very interesting thing about these results is that if you look at how the constraints on the neutrino mass change as a function of K max for the power spectrum on its own, so looking at this red line, you can see that the constraints saturate around Kmax of 0.2. And then you just have this flat line all the way to Kmax of 0.5, which is saying that as you go to smaller and smaller scales, if you just use the power spectrum, you're not going to get any extra information about the neutrino mass. However, if you compare with the halo mass function or the void size function or all of them together, then you get this decreasing line as the Kmax increases. So as you go to smaller and smaller scales, you get more and more information, all the way down to Kmax of 0.5 and potentially beyond. And so this is saying that there's really a lot of information in the small nonlinear scales when you combine all these higher order statistics. And in fact, there's a lot of these higher order statistics where people have found great constraints on the neutrino mass using bispectrum, Minkowski functionals, peak counts, probability density function, Mach power spectrum. And all of these different papers look at slightly different things. So not only at different higher order statistics, but also at different fields. So some look at lensing, some look at the matter field, some look at redshift space distortions. And so one very important question to answer is, where is the information coming from? Is there a particular higher order statistic which is really sensitive to neutrino mass, or is it coming from a particular choice of cosmological data? And so to start answering this question, what I've shown you so far is the information content of delta M, so the total matter field. And what this plot is showing is what I showed earlier, but now I've added two extra lines. The black line is now the marked power spectrum, and the yellow line is the linear power spectrum. And you can see that everything has very different degeneracies. So when you combine everything together, you can get very tight constraints on neutrino mass. But what if we looked at delta C instead? What if we just looked at the cold dark matter? Well, in that case, all the contours actually line up. And so this is saying that there's not that much information about neutrino mass in the cold dark matter field. Only when you combine cold dark matter with neutrinos to get the total matter field do you have this degeneracy breaking, and there's a lot of information about neutrino mass. And so the next question to ask is, what do surveys actually measure? So looking at this equation again, surveys don't measure delta nu. If they did, we'd have amazing constraints on neutrino mass. They also don't quite measure delta C. They actually measure halos and galaxies, which are a bias tracer of CDM. And so here I've just shown the equation for a linear bias model, but in practice, this could be much more complicated. And they also don't measure delta M. They measure lensing, and lensing is an integral of delta M over the line of sight. And so it compresses a 3D delta M field down to a 2D delta M field. And also there's this prefactor out of the front, which depends on cosmological parameters such as omega m. And so the question to ask really is, how much information is there about neutrino mass in the halo and galaxy field and in the lensing field? And so to answer this question, we ran two different simulations with the same linear physics. One simulation had massive neutrinos in it, which we call the real simulation, and one simulation had no massive neutrinos in it, which we call the fake simulation. So the key point here is that the linear physics is matched. We use the same linear initial conditions, and the only change is in the nonlinear effects due to massive neutrinos. And what we found when looking at the cross-correlation coefficient between these two simulations is that the matter field, so the green line, deviates from 1 on small scales between like k of 0.1 and 1, suggesting that there's a lot of information in the matter field about neutrino mass. But when you look at the halo and lensing field, this cross-correlation coefficient is 1 all the way to around k of 1, suggesting that there's almost no difference between the real and the fake simulations. And if there's no difference between the real and the fake simulations in terms of cross-correlation coefficient, that means that there's no nonlinear information. There's no information in the phases about neutrino mass on these scales. And so in conclusion, this is saying that the nonlinear effects of massive neutrinos at a single redshift can be faked by cold dark matter for halos and lensing. And if this cross-correlation coefficient is a bit complicated to understand, we can look at some higher order statistics in the real and fake simulation. And so what these plots are showing are the power spectrum, the void size function, and the Mach power spectrum, so the ratio between the simulation with and without massive neutrinos. And you can see that in all cases, the ratio is 1 all the way across the scales, suggesting that there's no difference between the two simulations. And so what does this mean moving forward in terms of measuring neutrino mass? How can we maximize the information about neutrino mass moving forward? And so one thing we can do is jointly analyze multiple redshifts and multiple traces to break degeneracies. So those previous slides were just at a fixed redshift, but neutrinos evolve differently to cold dark matter. So if you combine information from multiple redshifts, that can help break degeneracies and give you information about neutrino mass. And so one obvious way to do this is using CMBxLSS. We already spoke about stage 3 surveys, but now looking at stage 4 surveys, if you combine CMBS4 with LSST, so CMBS4 on its own gives you this gray line, LSST on its own gives you this green line. But if you combine them together, you get this orange line, which gives you much tighter constraints on the neutrino mass. Another way you can get neutrino mass information is using velocity information. So velocity traces the total matter field, which we saw contains information about neutrino mass. So if you have a way to probe velocities, then you can get tighter constraints on neutrino mass. And different ways we can measure velocities is through redshift space distortions, the KSZ effect, and also from supernovae. And what this plot is showing is that in redshift space, the ratio of the power spectrum from the previous experiment in the previous slide between the simulation with massive neutrinos and without massive neutrinos is a much higher ratio along the line of sight, which is where redshift space distortions take place. And so this is saying that there's information in the velocities. And then instead of looking at different physical effects, another way to try and extract as much information as you can about neutrino mass is to develop statistical methods to optimally extract information from cosmological data. And one way to do this is with field level inference. And so these are two things that I'm currently working on, but don't have time to go into a lot of detail about, but just to give a quick flavor of these two things. So in terms of CMB cross LSS, here's a nice cartoon of the CMB in the background and large-scale structure in the foreground. We know that large-scale structure on its own is very interesting. We know weak lensing surveys and galaxy surveys tell us a lot of information, but there's a lot of cool ways in which the CMB and large-scale structure interact and can give us even more information if we know how to model these effects. One such way is CMB lensing, where light from the CMB is deflected by matter on its way to us, and that leaves an imprint on the neutrino mass and also other cosmological parameters. There's also the SZ effect. So this is where photons interact with electrons on their way to us from the CMB. And this also leaves an imprint on neutrino mass and other cosmological parameters. But then there's also systematics going on. For example, galaxies just emit light. And here's a spectrum of a galaxy, a radio galaxy, and you can see that there's some radio emission, there's some infrared emission from star formation, there's also AGN emission, and just optical emission, which is why we see these galaxies. And so if you really want to measure anything using CMB cross LSS, you want a way to simulate all these different effects, to forward model the SE, lensing, galaxy emission, etc. And so this is something I've been working on in the half dome simulations, where we're building these massive simulations which simulate the universe all the way from the CMB until today, to the large scale structure today. And so this is very exciting. Stay tuned for more. These will be publicly available very soon. And then in terms of developing statistical methods to extract information, the idea of field level inference is to say that we know that the initial universe is described by a Gaussian random field. So if you look at any pixel in the initial universe, it will be described by a Gaussian random variable. And then nonlinear physics makes things more complicated. So you have some forward model like an n-body simulation or perturbation theory, which takes your initial universe S, every pixel in your initial field of the universe, and some cosmological parameters lambda, for example, sigma A, omega M, and gives you some final field like the galaxy field or the weak lensing field. And this will be very nonlinear. And the idea of field level inference is to take this nonlinear field that you observe and to rewind the clock back to the initial conditions of the universe. And so infer the initial conditions of the universe as well as the cosmological parameters on the way. And because you're doing this inference in terms of the initial conditions of the universe and the cosmological parameters, this should in principle give you the tightest constraints on the cosmological parameters that are possible. And so I think this is a really exciting approach to doing cosmological inference moving forward. And so unfortunately, I don't have time to go into these last parts of my talk, but I'd be very happy to talk about them more in the discussion. But for now, I'll just say that collaboration between cosmologists, data scientists, and particle physicists is really the way forward for us to measure the neutrino mass as best we can. Thank you.